what this theorem says is, so if we have a function which we know an antiderivative, then we can find a definite integral. There's a way to calculate the definite integral. Okay, suppose, so what I'm thinking is I'm given a function and I want to find the integral of this function. So in my mind I'm thinking a function that I can find, I have some sort of antiderivative of. So let's say I have x squared. I can do antiderivative of x squared, that's x cubed over 3. But then they want us to find the integral from, let's say, 0 to 1 of x squared dx. This, now because I have limits, this becomes a definite integral, which is the limit of some sum. So I have to do a summation and then take a limit of that as delta x approach to 0 or as n approach to infinity. That's how I would have to do this. But now this theorem will give me, oh, there's another way of doing it. You can find antiderivative. If you can't find antiderivative of the function inside, then there is a way to calculate this definite integral. And that's actually why we're using the same notation for two completely different notions. One is a completely different idea, this limit of a summation, and one is just antiderivative. Okay? So that's why we have these two different notations, these two different notions having pretty much similar notations, with the exception of the limits a and b. This looks almost like that one. So let's go right into it and write down the theorem, okay? So suppose f has antiderivative. Suppose f is, you can take any antiderivative, so that's why I'm antiderivative. Break, it doesn't work. Half or just some point. This is theorem that on this interval. Calculated by taking big F subtract big F at A. So big F at B subtract big F at A. A notation here, so we write as a help, as a notation, we write f of x evaluated antiderivative. You could use any antiderivative, okay? Then plug b into the function, and then plug a into the function and take the difference. That way you have the definite integral calculated. Instead of taking the whole summation sign and the limit as n approach to infinity, then you can actually calculate the integral. And it's a very, very important theorem. I won't prove it here, but it is a cornerstone theorem. That's why it's called fundamental. Okay, so if I'm going to look for antiderivative of x squared, that will give me x cubed over 3. And now I will evaluate that from 0 to 1. So that will give me 1 cubed over 3 minus 0 cubed over 3. So 0 cubed over 3 is 0, and cubed over 3 is 1/3. So that's 1/3. So I have the integral from 0 to 1 of x squared dx calculated without having to do all that limit and sum and partitioning and all that stuff. All right.